Hello world, welcome to Boolean Maths. Today we're going to be discussing rational functions, specifically though just the end behavior. As the title indicates, we're going to discuss end behavior asymptotes. The end behavior of a rational function typically takes the shape of a line, at least the ones that we're going to talk about. I'm not going to really get into the why behind them, like taking limits to infinity. That could be for another video. This is just to really get you prepared for looking at a rational function and being able to state that attribute. So let's get going. All right, so the first thing we're going to discuss what you'd call a proper rational function. A proper rational function has a degree in the numerator that's going to be less than that of the denominator. So that's just how you would identify it. When you have a proper rational function, when you look at it right away, you can just write down horizontal asymptote, y equals 0. The x-axis is your horizontal asymptote. So you would just state that. A classic case of that, and I just can't resist stating it, would be the function y equals 1 over x. Many textbooks will have you, when you're studying rational functions, look at that reciprocal function, as it's called, and do transformations on that. That's one class of rational function that's easy to move around. But I think a lot of you know what 1 over x looks like. It does something like this in quadrant 1, and something like this in quadrant 3. So as x is going towards infinity, that's going towards infinity, y is approaching 0. And I told you I wouldn't do limits, but you can see that's a classic case of a proper rational function. The degree of the numerator is really x to the 0th power, right? Degree of the denominator is 1, and the graph ultimately just gets really, really, really tiny, but like almost 0, but it's not quite there. So that's why you have a horizontal asymptote, y equals 0. The graph literally looks like y equals 0 when x gets really, really big. Okay, so some examples of proper rational functions would be the ones that you see stated below here. So we have this one. Again, degree of the numerator is 2, degree of the denominator is 3. So y equals 0 is our horizontal asymptote. This function right here, the degree of the numerator is 1, denominator is 2. And this last one. So this one is in factored form. So, but it is proper, and if you're paying attention to this, you'll note, or you'll see that this is really the degree of that function is x squared plus, blah, blah, blah. I'm not going to expand that right now, but we know that the degree of the denominator is x squared, degree of numerator is x. So ultimately that is a proper rational function. And, I didn't mention this at the beginning, but proper rational functions are just like proper fractions. So, like 3/4, that's a proper fraction, right? Because the numerator is actually a smaller number than the denominator, which makes sense as far as fractions go because it's a part of a whole. If I had something like 5/4, that's an improper fraction, right? You'd be like, oh, well, that's 1 and 1/4, right? Because now I have 1 whole and a fourth. So so numbers, fractions that are written polynomials that are written as fractions, right? Polynomial divided by polynomial, your rational function, abides by the same rules, right? So then if the numerator is lesser in degree than the denominator, you have proper. Now, if the degrees match, that would be an improper fraction. Believe it or not, even if I had, 5/5, that's considered a fraction, right? But it's also really a whole number. It's just 1. So that's still technically an improper fraction because it's not representing part of a whole. So that leads us to our next slide and our next example. So our next example of rational functions, or the end behavior of a rational function, would be when it's an improper rational function, and the degrees of the numerator and the denominators match. Now, if you notice the theme here is we're constantly looking at the degree of the numerator and the degree of the denominator. So if the degrees match, we have actually another horizontal asymptote, and the horizontal asymptote is nothing more than the ratio of the leading coefficients. So you would look at, say, this is a generic polynomial, and if the degree is of the numerator is n and the denominators is m, right? So you'd say if n is equal to m, right? If your degrees match, they're the same, then your n behavior model, is in this case would be, again, a horizontal asymptote, will be in the form of a over b, the ratio of the leading coefficients. So that's the definition. So your horizontal asymptote for any rational function where the degrees match, just ratio of leading coefficients. So perfect example of that over here would be this first one. So you notice that the degrees, they match, right? They're both degree 2. So the leading coefficients in this case are going to be 3 and 1. So I'd say I have a horizontal asymptote at y equals 3 over 1, or just y equals 3, okay? Why don't you pause the video now and see if you can figure out the n behavior model or horizontal asymptotes for the next two. Okay, welcome back. All right, so the next one, degree of numerator is 1, denominator is 1. Leading coefficients are 5 and 1, so we have a horizontal asymptote at y equals 5. And this last one, degree of the numerator is 2, denominator is 2, so we have matching degrees. So we have a horizontal asymptote at y equals 3/2. Okay, so that was case 2. By the way, I didn't mention this before. I kind of mention this a lot in my videos, so I just want you to pretty much always do this. When you go to graph something, they tell you to graph by hand. It's not a bad idea, though, to go onto Desmos and see if you're right, or use your graphing calculator. I like Desmos because it's on a computer and it looks better. Get more detail. So I would take any of these. I bet you the third one right here. I'd plug this into Desmos, the function, and then also graph the line y equals 3/2 and see what happens. You'll see that the graph on its ends merges with 1.5, y equals 1.5, that horizontal line. So it might be approaching from the top on one side and coming up from the bottom on the other, but you should look at it. It kind of makes it more real for you. Okay, so this is going to be our last example here. This is funny. I'm just going to add a page at the end because it's it wasn't going to the top of the screen. All right, now there's another case with improper rational functions, when the ones that interest us the most. There's obviously a bunch of different scenarios, but when the degree of the numerator is greater than that of the denominator by only 1, so their difference is just 1. So and when that happens, your n behavior model, this got cut here. I should have paid better attention on when I made this. But your n behavior model is going to be y equals the quotient of long division for the numerator and the denominator. So I'm going to show you how to do that right now. But it's literally y equals the quotient. You don't have to worry about the remainder or remainder over divisor, nothing like that. It's just going to be y equals the quotient. So in this one in particular, I'm going to I would like to graph it and demonstrate to you how that works. So let's actually just take even a look at the graph of this rational function. So we're going to open up Desmos here and pull up this other problem, oblique asymptotes. Okay, so so here you can even see that the n behavior of this rational function is not a horizontal line. It's something that's more angled. All right, so I'm going to come back over here and then say we need to long divide this scenario. So I may have this on my clipboard. I don't think I do. I don't. All right, so I'm going to just write this out. So we want to divide x squared minus 3x plus 2 into 2x cubed plus x squared minus 8x minus 4. All right. So as you've probably learned, you ask yourself, what do I multiply x squared by to get 2x cubed? And we know that that's going to be 2x. So then I multiply 2x to x squared, I get 2x cubed, minus 6x squared, and then plus 4x. And then, of course, we go through it, minus, plus, minus. We have 7x squared minus 12. I don't know what just happened there. It was pretty fascinating. Minus 12x. And then we bring down that negative 4. Start the process again. What do I multiply x squared by to get 7x squared? Plus 7. So we have 7x squared minus 21. That same thing's happening again. There's definitely a little glitch here. Minus 21 x, and then plus 14, minus, plus, minus. Now, like I mentioned earlier, it doesn't really matter what my remainder is. I know what my quotient is. So, I mean, I just can't resist. I'm going to finish this and get negative 18. I'm going to leave that there. But what I'm really interested in is this. So for this problem, I would say I have an oblique asymptote, oblique, an oblique asymptote at y equals 2x plus 7. So when I go to graph this, I'm going to see that I would actually draw 2x plus 7 as a dotted line, and I'm going to see that the end behavior of this function should merge with the line. It doesn't ever reach it necessarily, but it's going to look like the line to y equals 2x plus 7. So here's our graph. I'm going to say, give me a new function, y equals 2x plus 7. I'm going to also just make sure that I'm just going to color code these so that they're more consistent with my graph. And sure enough, you see here. Let's take that full screen. There's the function, and there's the that blue line is the end behavior model, or the oblique asymptote. So if I just even pan out, I'm not going to even pan out that much, because you can see very rapidly the graph approaches, that red graph is approaching the blue asymptote. If I zoom in, you can see it just infinitely gets closer and closer and closer, but doesn't actually quite reach it. Likewise, if I go to the other side, the left side here, as x is approaching negative infinity, going left, it's y is getting, the graph is getting closer and closer to the line y equals 2x plus 7. So yeah, so from a distance, they look like they're the same thing. Anyway, that's end behavior. All right, so in summary, what we did was we talked about there's 3 cases. You have, and all of them entail looking at the degree of the numerator and comparing it to that of the denominator. When it's a proper rational function, when the degree of the numerator is less than that of the denominator, y equals 0. When the degree of the numerator matches that of the denominator, y equals the ratio of the leading coefficients. That's going to be your horizontal asymptote and behavior. The first two, both horizontal asymptotes, y equals 0 and y equals ratio of leading coefficients. And lastly, when the degree of the numerator is exactly 1 higher than that of the denominator, and it has to be bigger on the numerator, right? It's improper. You long divide in the quotient, y equals the quotient is going to be your end behavior model, or your what you would call an oblique or a slant asymptote. Anyway, thanks for tuning in. Hopefully that was helpful and clarified. Look for more detailed videos into graphing rational functions that will kind of bring all of this together. And hopefully that'll just make this not as challenging as it seems. Anyhow, take care.